Okay, in the last video where we worked a Bode plot example, we had h of s is 1000 over s plus 20, s plus 50. So what I want to do in this video is I want to see what happens if we put an s in the numerator. Okay, so this is going to change. Even though it seems like a very small change, it's actually going to change considerably what the Bode plot looks like. So let's just page back up to the previous example. Here's the function plotted, the magnitude and phase plot for when we had 1000 over s plus 20, s plus 500. Now we're going to add an s in the numerator. So what that changes is the low frequency asymptote. So let me first of all we'll show the magnitude plot and also the phase plot. So let's make this omega equals 1 again, and 10, 100, 1000. Once again, we won't worry about the labeling of the vertical axis, realizing it's in units of 20 dB per decade. So we'll put some tick marks here to illustrate the 20 dB per decade, and then down here at the bottom we'll plot the phase of h, and we'll use the same horizontal axis, but here we'll have tick marks in 90-degree increments. Once again, we won't label that quite yet until we're close to being done. Okay, so the first thing we look at is starting a new problem here. The first thing we want to look at is the low frequency asymptote. So low frequency asymptote. That's determined once again by whether you have poles or zeros at 0. So we ask, this should be 500. 500. So that's determined by whether or not we have poles or 0 at 0. So let's first of all label our zeros or our poles. We had one at 20 and we had one at 500, just like the last problem. And then notice we are going to have a low frequency asymptote. Because of this s, it's not going to be equal to 0 dB per decade. So as we know, if we have a term like s to the n, that corresponds to the slope of 20 n dB per decade. So in our case, n is equal to 1. So our low frequency asymptote, kind of trying to sketch my plot here, is going to have a positive slope of 20 dB per decade. Now note that will never flatten out, because these s to the n terms determine what happens as you approach 0 in omega. Even though on a log plot, semi-log plot, we never fully approach 0, or we never fully get to 0, but we do approach 0. So this is just the behavior of this transfer function at low frequency. Now, as we know, when we encounter our first pole, that has the effect of subtracting 20 dB per decade from the slope. Let me try to flatten that out a little bit better. It's actually pretty hard to draw a straight line on these tablets. Alright, so this then would be between 20 and 500. I would have had my previous slope, and I would have subtracted 20 dB for this pole. So this will be 0 dB per decade. And then for 500 and greater, because 500 is my highest frequency cutoff or highest frequency critical frequency, I'll subtract another 20 dB per decade, because that is another pole. So each successive pole subtracting 20 dB per decade. So you can see here what I have is I have actually a bandpass filter. Okay. Looks like that. Now to find the gain is a little bit different here, because in the previous example we took the transfer function directly, we let s go to 0, and that worked pretty well. So we can't do that here because we have 0 in the numerator, which would give us an incorrect result. So instead, what we want to do is work with our transfer function a little bit. Let me come down here. So I'm going to take my 1000 s, and I'm going to factor out a 20 from the first term and a 50 from the second term. And so that's 1,000 over 10,000 times S over 20 plus 1 S. I'm sorry, I keep saying 50, it's 500. Don't know why I got 50 on the brain. S over 500 plus 1. Okay, so that's 10 to the minus 1 times this stuff here. Now we're going to make the assumption, okay, that when omega, so S goes to j omega, okay, and then we take the magnitude. So the numerator, the magnitude would be just omega, and we're going to assume that we're going to find this at omega equals 1. So we're going to come to the low frequency asymptote, and this is why I put my vertical axis at omega equals 1, because it makes a good guide to the eye when you have this kind of situation. Okay, so if I were to take the log of this whole thing, if I were to substitute j omega, take the log of the absolute value, then I'm going to get a sum. I'm going to get a sum of a gain term, log of 10 to the minus 1 times 20, plus 20 log of all this other stuff, okay? Now all this other stuff at omega equals 1, this numerator is going to make 0 contribution, and these denominator terms are going to be very close to 1 because S is small, or omega is going to be small compared to 20 and 500. So you're making the assumption that the only term that contributes at omega equals 1 to the low frequency asymptote is the gain. Okay, and we've already shown that this is 2. So that would mean right here on the omega equal 1 axis, this is 2 dB. Okay, which would make this maybe about 4, 24, etc. Okay, so that's how you do it when you have a 0 at 0. The phase is going to be different because the low frequency on the phase will start at 90 degrees. So we'll start at 90, and then at 20 we will drop to 0 phase, and then at 500 we will drop to negative 90 phase. And so our plot, because right now all we plotted is the asymptotes, so on the magnitude it'll look like this. Good until I get to this last little part. Magnitude is going to look like this, and the phase, it departs a little sooner, it goes right through the middle,